Swayam Prabha. Digital India. Educated India.
Welcome back. We are going to continue with our discussion on various types of operations and matrices. One of the most important thing is solution of linear systems. It is believed that 70 to 75% of all the computations all over the world done by every scientist involve solving linear systems. Whatever problem you have been solving, the mathematical technique tells you to reduce the problem to one of solving a linear system. So ultimately the problems are reduced to solving linear system. So solution of linear system is one of the fundamental pathways to computation in all of sciences and engineering. Is a very important topic. So I would like to be able to talk about the existence of solutions of linear system. Ax is equal to b. A is a square matrix n by n, B is a n vector, x is the unknown. So A is given, B is given, x is not known. In order that the solution exists, I want you to look at one condition. We generally don't look at it this way. So let's look at this now. So this is a copy of Rn. This is a copy of Rn. Here is a B. I want an x here. I want an A such that Ax is equal to B. All of it with me? That's right. So when will the solution exist? The solution will exist only when B belongs to the range of A. Are you with me? That means there must exist some x for which B must be an image. So if B is such that there is no x for which B is the image under A, then there is no x. And that's the definition of a range that we talked about a few slides ago. So a necessary condition for the existence of a solution Ax is equal to B is that B must lie in the range of A. So if B lies in the range of A, then there exists an x such that I can express B is equal to A of x. Are you all with me now? That's the idea. Secondly, I want the solution to be unique. Under what condition solution is unique? The determinant of A is not 0. So A being non-singular. If A is non-singular means what? The range of A is whole of Rn. Are you with me, please? If A is non-singular means what? Its rank is n. If rank is n means all the columns are linearly independent. So every linear combination of the linearly independent columns must span the whole space. So given B, there exists a vector x such that x will be equal to B. So what are the necessary and sufficient conditions for Ax equal to B to have a solution? A must be full rank, or the determinant of A must be non-zero. If the determinant of A is non-zero, then there exists a unique solution. There is something in between. I will come to that in a minute. So if A is non-singular, Ax is equal to B has a unique solution, which is x is equal to A inverse B. This is simply a mathematical way of writing, but we need to be able to compute the inverse. when we are going to be solving least square problems, I am going to talk about algorithm to exactly to do this. So there are two types of linear system. One is Ax is equal to b, another Ax is equal to 0. This is called the non-homogeneous equation. This is called the homogeneous equation. So a non-homogeneous linear system has a unique solution if and only if A is a full rank. So what is the condition for a homogeneous system to have a unique solution? Look at, please go back to the definition. What is the null set of A? Null set of A is a set of all x such for that A times x is 0. With me? If A is a full rank, all the columns of A are linearly independent. If all the columns of A are linearly independent, Ax essentially tells you linear combinations of the set of all linearly independent columns. In which case Ax can be 0 only when x is 0. So Ax is equal to 0 has a unique solution x is equal to 0 when A is non-singular. When I say a solution, I always mean a non-null solution. I always mean a non-trivial solution. So Ax is equal to b has a non-trivial solution when A is non-singular. Ax is equal to 0 has a non-trivial solution when A is singular. That means the columns of A must be linearly dependent. If the columns of A are linearly dependent, then there exists a set of coefficients by which I can multiply each of the columns and annihilate and create a 0. Everybody with me, please? So these are two complementary conditions. So the non-homogeneous system has a unique solution when A is non-singular. The homogeneous system has a non-trivial solution when A is singular. All with me? These are two important things to consider. So when you have A, you also have A transpose. So I would like to talk about now A transpose. So let's look at a couple of things now. So you remember A is m by n, I have Rn, I have Rm. This is the null space of A. This is the range of A. You remember that? The same picture holds good even when m is equal to n. Even when m is equal to n. So this is the mapping from here A. The mapping from here to here is A transpose. With me? A transforms n vectors to m vectors. A transpose transforms m vectors to n vector. So much like the null space of A, the range of A transpose also its range, its null space. So the range of A transpose and the null space of A transpose. So Rm can be divided into range of A and the null space of A transpose, or Rn can be divided into range of A transpose and the null space of A. So these are the four subspaces which are of great interest in linear algebra. Are you with me? A transpose. A transpose is rectangular, A is rectangular. If whatever happens to A must happen to A transpose. Every matrix has a range, every matrix has a null space. So I am going to be talking about the range in the null space of A and A transpose. Everybody? Good. So what is the null space of A transpose? It is a set of all y's such that A transpose y is 0. So y is here. X is here. So if B belongs to the range of A and y belongs to the null space of A transpose, then B transpose y is Ax transpose y. B is with me. Ax is equal to B. That's what's given to me. That's equal to X trans. That is X. This will be X transpose A transpose y, and that must be 0. Why? A transpose Y belongs to the null space of A. Are you all in my place? So that's an important time. Therefore, the range of A and the null space of A transpose are mutually orthogonal. That's essentially what it is. That's essentially what this relation essentially tells you. So this is a fundamental result in linear algebra that's called Fredholm's alternative. Given a matrix A is m by n, that's what this picture is all about, then exactly one of the two statements are true. Either Ax is equal to B has a solution, or A transpose Y 0 has a solution such that Y transpose B is not equal to 0. I want you to think about that. So this is the general relation for the existence of solution of Ax is equal to B when in general A is m by n. The special case of that occurs when m is n. M is equal to n, that is A is equal to m by n, and that's what we talked about here to start with. So this is for the square system. This is for the general m by n system. With me? And for the square system, I know the solution. For the m by n system, there is this notion of what's called alternative. One of the two things hold good, and that verification I have already given here. Now I am going to introduce you to two other concepts that arise from matrix theory. One is called the bilinear form, another is called the quadratic form. Let A be a m by n matrix. I am going to define, given A, given two vectors x belonging to m, y belonging to n, such that the function takes two input and creates an output which is x transpose AY. So what is x transpose AY? X is a column vector, x transpose is a row vector. This is A, this is column. So this is a constant. So f of A x comma y is x transpose AY. X belongs to Rm, y belongs to Rn. That's called the bilinear form. Why this is bilinear form? This function is linear in x, this function is linear in y. Simultaneously linear in two variables, bilinear. Are you with me? So given A, I can, what does it do? It maps the vectors from Rm and Rn simultaneously. So there are two vectors given, one from Rm, another from Rn. F of A x comma y is x transpose AY, and that's a scalar. Are you with me now? Bilinear form. Now I specialize. A is m by n. F of A Rn to Rn. So I am now going to define Q subscript A of x, which is x transpose Ax. With me? Do you see the difference between the two? A is square. I am going to replace x with y with x. So instead of x transpose Ax, I got x transpose Ax. Here it is linear in two variables. For example, if I consider xy as a product is quadratic, but it is linear in x and linear in y. If I consider x square, it is quadratic. This is quadratic, this is quadratic. I call it this is quadratic, I call it this is bilinear. So you know the difference between linear, bilinear, quadratic, and so on. So what is this? This is called a quadratic form or a quadratic function. So what is a quadratic function? It's a polynomial of degree 2 in multiple variables. So I'm now going to give you an example of a quadratic function. Let n be 2, let x be x1, x2. I'm working in a 2D plane. I have a matrix A11, A12, A21, A22. I'm not assuming anything other property, the general property. So if I'm considering x transpose Ax, with me? So what is that? x1, x2, A11, A12, A21, A22 times x1, x2. If you multiply this, what do I get? A11 x1 square, A12 plus A21 x1, x2 plus A22 x2 square. And that's what's called the quadratic function. So in one variable, what are the quadratic functions? I have a quadratic function x square is a quadratic function, Ax square is a quadratic function, Ax square plus Bx is a quadratic function, Ax square plus Bx plus C is a quadratic function. This is homogeneous. This is second and first degree. This is the second, first, and constant degree. So what is this? This is the homogeneous part. It's a homogeneous polynomial in two variables of degree 2, because there is no other term. Every term is of degree 2. This is degree 2, this is degree 2, this is degree 2. Everybody? So do you now see the difference between quadratic forms and bilinear forms? In optimization theory, the cost function is always a quadratic function. Why quadratic function? The simplest quadratic function is x square. With me? If I have ax square plus bx, what is that it can do? It can shift it like this. If I add a constant, what is that it can do? It can probably shift it like this. Quadratic is quadratic, it doesn't change. Everybody? What is the property of quadratic function? It's a unique minimum. So in optimization problem, we want to make sure the minimum exists and the minimum is unique. In linear system, we wanted to make sure the solution exists and is unique. If you don't know the solution exists, how do I find it algorithmically? If you don't guarantee it is unique, how do I chase it around? Are you with me? Are you all with me, please? So, important thing before you start any computational problem is formulate the problem. Ask first the question, does the solution exist? Is it unique? If it doesn't exist, you are out of business. You screw up the problem. You change the problem to make sure it exists. Then if it exists but not unique, again you screw up the problem. Go back and modify the problem to make sure the solution exists and is unique. I want you to understand, if it is a non-unique solution, an algorithm can only march towards one solution. So multiple minima problem is a very difficult problem to solve. Knowing that multiple minima is a very difficult problem to solve in optimization, we want to make sure that the cost function has only one minimum. What is the standard cost function that guarantees unique minimum? Quadratic function, where the matrix A is SPD, symmetric and positive definite. So the matrix of the quadratic form is symmetric and positive definite. Then the quadratic function has a unique minimum, and that's the generalization of the parabola. What is the definition of parabola? Ax square, A must be greater than 0. So Ax square is replaced by x transpose Ax. Here A must be greater than 0. Here this A must be SPD. That's all the condition. Do you see that, please? That's the analogy. So what are the properties of quadratic function? I define the quadratic function for any matrix, right? Now I'm going to talk about some of the consequences of that. So QA is x transpose Ax. X transpose Ax is a constant. What is the property of a constant? The transpose of a constant is itself. Everybody? 3 transpose is 3. The transpose of a scalar is itself. So if this is a scalar, it is equal to transpose, but the product of transposes can be expressed as the product of the transpose of the reverse order, which is x transpose A transpose X. So look at that now. We have found out that x transpose Ax is the same as x transpose A transpose X. So if this is QA of X, this must be equal to QA transpose of X. So what is it we have now shown? The value of the quadratic form for the matrix A is the same as the value of the quadratic form with A transpose. Are you all with me now? It's a very important consideration. So if these two are same, if I add the two, this is QAX, this is QA transpose X. So QAX is equal to 1/2 of QAX plus QA transpose X. Everybody please. But QAX is x transpose A, X. This is x transpose A transpose X. X transpose is the left common factor, X is the right common factor. I can bring in 2 inside. I can rewrite this as this expression, x transpose A plus A transpose by 2 times X. Everybody? Do you remember a few slides ago I said the symmetric part of A is A plus A transpose by 2? That this is equal to AS, X transpose AS, X. Wow. So what does this tell you? The value of the quadratic function for any matrix is the same as the value of the quadratic function with the symmetric part of that function, symmetric part of the matrix. So without loss of generality, from now on, I will assume the matrix of the quadratic form is always symmetric. Because if it is not symmetric, I can compute the symmetric form, symmetric part of A and replace A by symmetric part. So that's what we have done, right? So what is this? This is Q of AS of X. So Q of A of X is equal to Q of A of X, AS of X. That means A is not important. It is A subscript S is important. A subscript S means symmetric part. The symmetric part of A is a symmetric matrix. Are you with me? So what is the general theory? We are interested in quadratic function only for symmetric matrices. There is no theory of quadratic forms of non-symmetric matrices. It's a very powerful result. Are you with me? If you give me a general matrix, all I need is a symmetric part. Therefore, without loss of generality, from now on, we will assume QA of X, the quadratic function, only for symmetric matrices. That's a very important part. Therefore, when you do optimization, you need to talk about quadratic forms. The matrix A is we require it to be symmetric and positive. Why positive definite? Well, hold on, I will come back to that later. So the role of symmetric matrices in quadratic function, and quadratic functions play a fundamental role in optimization. So you can see the link now. Everyone? That's right. Now I'm going to go to positive definiteness, which I have not defined, which I am going to define properly. I don't know how many of you may have heard of, I don't know how many of you know the definition, so I'm going to start with the definition. Let A be a n by n matrix. A is said to be a positive definite matrix. Without loss of generality, I can assume A is symmetric. Why? I'm interested in quadratic forms. Quadratic functions means A must be symmetric. So let A be a symmetric n by n matrix. A symmetric n by n matrix A is said to be positive definite if X transpose AX is greater than 0 for all X not equal to 0. It is equal to 0 only when X is 0. Let's think of the analogy now. So f of A of X is equal to AX squared. A is positive. If A is positive, AX squared is 0 only at X is 0. Everywhere else is positive. Everybody with me? So A being greater than 0 is a condition for AX squared to be positive for all X except X is equal to 0. That's for the single variable. For the multivariate, what is the corresponding condition? The matrix A must be positive, definite. So what characterizes so this is the definition of positive definiteness. This definition is good but is useless. Why? To use this definition to check for positive definiteness, I have to check for every X. How many X's are there? There are infinitely many. So some definitions are basically infinitary in nature. They are good concepts, but they cannot be used to check it. There is no algorithm based on that can solve the problem in finite time. So I need to look for equivalent conditions that I can check in finite time. With me, all of you with me, please? That's right. So this is the generic definition. So what are the equivalent definition? So given A, you all know the principal minors, right? How many of you with me? If you have a 4 by 4 matrix, every element along the diagonal is a principal minor. Then 2 by 2 principal minors, 3 by 3 principal minors, 4 by 4 principal minors. With me? Come on, guys. What is the principal minor of order K? A principal minor order K is a submatrix with K rows and K columns whose principal diagonal coincides with the principal diagonal of the original matrix from which this is picked up. With me? So a matrix has several different types of principal minors. Order 1, order 2, order 3, order 4. order n minus 1, order n. There are n principal minors of order 1, each of the diagonal elements. There is only one principal minor of order n, the matrix itself. With me? I can compute the number of principal diagonals, essentially. So what is an equivalent definition? A matrix is said to be positive definite if and only if the principal minors of all orders are positive. Minor means what? Is the determinant. The determinant of the principles of matrix. That's a principal minor. With me? So every minor of order 1, 2, 3, okay, up to n must be non-singular. That's one way. Another way would be the eigenvalues must always be positive. With me? I can compute the eigenvalues, I can check. I can compute the principal minors, I can check. But this original definition by itself, while it makes a lot of sense, cannot be used in checking. Are you with me now? So to understand the condition, so every property of a matrix tries to restrict the elements of the matrix. With me? Any matrix, the elements can be anywhere. Non-singular matrix, there is a restriction, right? The determinant must be non-zero. Symmetric matrix, upper half must be equal to the lower half. Orthogonal matrix. With me? So every property tries to put a restriction on the structure of the matrix. So I want to understand the structure of the condition that positive definite brings in. So let A, B, B, C be a symmetric matrix. QAX, which is X transpose AX, is given by this quadratic function. You all have learned to perfect the square. You remember that? So you can express this by perfecting the square. A times x1 plus b by a x2 whole square plus c minus b square by a x2 square. Please verify this. This technique in algebra is called method of perfecting the square. So this function is essentially this. Now let's look at this now. First one. For this to be positive, look at this now. x1 plus b over a x2 whole square. Any square quantity is positive. So for the first term to be positive, a must be positive. For the second quantity, the product of 2, x2 square is always positive. So its coefficient must be positive. With me? So this quadratic function is positive when a is positive, c is greater than b square by a. So that is equal to ac must be greater than b square. And I also want my c to be positive because that's a principal minor of order 2. So a must be positive, c must be positive. The determinant of this, what is this? ac minus b square. If ac minus is greater than 0, this means ac minus b square must be positive. So this is principal minor of order 1, principal minor of order 2, principal minor of order 2. Everybody? So that matches that. Therefore, a symmetric matrix AB, BC is positive definite only when A is positive, C is positive, and AC is greater than B square. Are you with me now? That's right. So symmetry has its own restriction. Positive definite brings another restriction. So every property tries to reduce the values that the elements can take. Understanding this is the secret to appreciating some of the tools in linear algebra with respect to applications. All of you? Come on, guys. I'm talking about a one semester course in 2-3 lectures, trying to bring out all the essence of it. Because you all have had some exposure to linear algebra, but I'm trying to help you to be able to unite all the thought processes. Next is eigenvalue, eigenvectors. Let A be a n by n matrix. So what is the idea here? If x is a vector, if A is a matrix, if y is equal to ax is equal to b, y is equal to ax, in general y will be a vector different from x. In general, y is transformed x, the transformation can elongate it, can rotate it. The length of y may not be equal to the length of x, with me? And y also has a rotation with respect to x. We have seen that. That's the general operations and so on. Now I want to ask myself the following question. Does there exist a direction x such that ax is proportional to x? Are you with me? Proportional to x means what? Is a constant multiplier is equal to lambda times x. Multiplying a vector by a constant means what? It's simply scaling. The direction doesn't change. So what does this equation tells you? When I multiply a vector x by a matrix A, it doesn't change the direction, it simply scales it. That means Ax as a vector rides along the same direction as x. That means the direction x is invariant under the transformation Ax. But it doesn't rotate, it only scales. Now two things now, we have already seen. Orthogonal transformation only rotates but not scale. Here I am looking at, given a matrix, does there exist a direction such which there is no rotation but only scaling? Do you see the complementary? So such a direction is called eigendirection or characteristic direction. Eigenvalue, eigenvectors come from German origin. So lambda is called eigenvalue, x is called the eigenvector. So if there exists a vector v such that and a lambda r, av is equal to lambda v, then lambda is called the eigenvalue and v is called the eigenvector. So eigenvectors are called invariant direction. Invariant means what? The direction doesn't change under the operation of the matrix A. Everybody? So AV, so if that is the case, AV is equal to lambda V. So if I bring it here, this is AV minus lambda IV is equal to 0. Everybody please. It becomes a homogeneous equation. Now we have already seen a homogeneous system has a non-null solution only when it is singular. You remember 2 slides ago. So the determinant of A minus lambda I must be 0. Come on guys. The determinant of A minus lambda I is called a polynomial P lambda. That's the determinant. That polynomial is of degree n because A is an n by n matrix. So that polynomial is called characteristic polynomial. It's a polynomial in lambda. Fundamental theorem of arithmetic essentially tells you an nth degree equation will have n roots. The n roots are real. If they are complex, it must be a complex conjugate because the coefficients are real. So lambda 1, lambda 2, lambda n be the n roots of that. Lambda i's are real or complex. Complex root occurs in conjugate pairs. Okay, good. Now comes the basic, another interesting thing. So before I go further, this is the general knowledge about the eigenvalues or eigenvector. So in general, for a given matrix A, the eigenvalues could be real or complex. Therefore, the eigenstructure of the complex plane, this is the real, this is the imaginary. So what is the distribution of eigenvalue for a general matrix? It could be this. It could be positive, 0 or negative. It could be this. It could be that. Everybody with me please? There are points in the complex plane. Points in the complex plane lie either in the x-axis or if they are outside the x-axis, they will occur the conjugate pairs above and below, symmetry. Now, when I say the matrix A is symmetric, the lambdas are real. So for a symmetric matrix, the eigenvalues are only these. In addition, if I say the matrix is symmetric and positive definite, the eigenvalues are all positive. All of me please? I have a module where I can prove all these things. I don't know whether I'm going to do it now or maybe later, but there are lots of other topics I need to cover. I don't want to stuck in matrix theory. Everybody? Therefore, the general eigenstructure for a general matrix, the eigenstructure for a symmetric matrix eigenstructure for a symmetric and positive definite matrix. With me? So an example, I am taking a symmetric matrix. Look at that, 5 is positive, 8 is positive, 5 times 8 is 40, 2 times 2 is 4. So AC minus B square is positive. I computed the polynomial. The polynomial has 2 roots. Everybody please verify. As I told you in the last class, you should believe the teacher but not too fully. You should be skeptical. You should verify everything your teacher says. With me? That's right. So verify that the eigenvalues are 9 and 4. Once I have eigenvalues are 9 and 4, I want to be able to solve the linear system A minus 9I times x is equal to 0. I also want to be able to solve A minus 4I times y is equal to 0. The solution to this x and y, in general you get x and y as vectors. Everybody please. Here I am only interested in the direction, so I want to be able to find x and y as unit vectors. So the 2 unit vectors v1 corresponding to lambda 1, v2 corresponding to lambda 2 are given by these. Are you with me? There is an additional property. The eigenvectors corresponding to distinct eigenvalues are also orthogonal. v1 is orthogonal to v2. With me? So there are lots of computational things. 2 by 2 system, I always tell my students, you have to be able to solve simple problems by hand. Unless you solve simple problems by hand, you don't get that aha feeling. Yes, I can do it, and now I know. So I would like you to verify all these things, please. With me? So let A be a SPD matrix. Let lambda I vi for I is equal to 1 to n be the collection of eigenvalues and eigenvectors. Everybody? Now I can see there are n eigenvalues, there are n eigenvectors. I can collect all the n eigenvectors to be a matrix V. So V is a n by n matrix of n eigenvectors. Lambda is a diagonal matrix of n eigenvalues. Lambda 1 V1, lambda 2 V2, lambda n Vn. Everybody? Therefore, AI Vi, this is an element wise. Collectively, I can represent A is equal to V lambda V transpose. AV is equal to V lambda. Lambda is diagonal. And when the matrix is symmetric and positive definite, the eigenvectors are orthogonal. That's a property. I have verified it. I didn't prove it, but verification. Therefore, if I multiply AV is equal to V lambda, if I multiply on the right by V transpose is equal to V lambda V transpose, but this is identity because orthogonal matrix. So A is equal to V lambda V transpose. With me? And that can be written as summation lambda I Vi transpose. Look at that now, Vi transpose. Vi is the column, Vi transpose is the row. That's an outer product matrix. So this is just a decomposition of A. This decomposition is called spectral decomposition of A. Spectral decomposition. Why this is spectrum? The eigenvalue, the set of all eigenvalues constitute the is called the spectrum of A. Why spectrum? Well, that's the name it's given to by mathematicians. The eigenvalues reveal lots of properties of the matrices. With me? So that's called spectral properties of a matrix. Spectrum of a matrix. Spectral decomposition of a matrix. And this is the multiplicative decomposition. Why this is the multiplicative decomposition? A is expressible as a product of V lambda V transpose. I want to give you an analogy now. In number theory, there is a multiplicative decomposition. What is that? Every composite number can be expressed as product of powers of prime. 25 is 5 square. 32 is 2 to the power of 5. With me? That's right. So that's called multiplicative decomposition using prime numbers. In matrix, I can also decompose the matrix and as I express the product of matrices. So mathematicians ask a question, if I can do this number theory, can I do in matrices? What different kinds of multiplicative decomposition are possible in matrix theory? Spectral decomposition is the mother of all decompositions. It's a fundamental decomposition technique. With me now? How many of you have heard of singular values? So we talked about eigenvalues, eigenvector decomposition, multiplicative decomposition. And I also want to do one more before I go further. So AV is equal to V lambda. So if I multiply this by, on the left side, V transpose A is V transpose V lambda, that is equal to lambda, because V is orthogonal. So what is it I have done? I have expressed V transpose AV is lambda. But what is V transpose? V is orthogonal, right? So this can be V inverse AV is equal to lambda, because V transpose is AV. You remember similarity transformation we talked about? That means every symmetric positive definite matrix is similar to a diagonal matrix. You remember that? Now you would also remember that I talked about B transpose AB as a congruent transformation. You remember that? We defined. So you can think of this as a congruent transformation. You can think of this as a similarity transformation. In this particular case, similarity transformation and congruent transformations are the same. So what does this tell you? Every matrix can be expressed in a canonical form, the simplest possible form. The simplest possible form is a diagonal form. So using eigen decomposition, I can transform a matrix to a diagonal matrix, where the diagonal matrix consists of only the eigenvalues along the diagonals. So what does this tell you? The eigenvalues can replicate the action of A. Are you all with me? Eigenvalues are so important. Diagonalization is an important property. I am also relating the congruence transformation, similarity transformation, orthogonal transformation. Everything is coming together beautifully. And that's the thing I would like you to be able to enjoy. I hope you do. Now singular values. If A is a non-singular matrix, I have two Gramians, A transpose A and A transpose. This Gramian I would like to be capital G. They are symmetric matrix. If A is non-singular, both of them are symmetric and positive definite. So if it is symmetric and positive definite, it must have an eigenvalue. Let lambda I be the eigenvalue of A transpose. A transpose A. So A transpose A Vi is lambda I Vi. It must have n eigenvalues. If it is positive definite, even the least eigenvalue must be positive. Lambda 1 is the most eigenvalue, lambda n is the least eigenvalue. They are ordered lambda 1 to lambda n like that. With me? Now I would like you to do the following. Look at this now. A transpose A transpose A transpose A Vi is equal to lambda I Vi. That means lambda I Vi are the eigenvalues and eigenvectors of the Gramian A transpose A. I would like to be able to find the eigenvalues and eigenvectors of A transpose. It can be shown that if I define Ui to be equal to 1 over square root of lambda I A Vi, A transpose Ui is equal to lambda I Ui. That means both A transpose A and A transpose share the same eigenvalues. The eigenvectors are related. The eigenvector of A transpose A can be converted into eigenvector of A transpose by this linear transformation. With me? Vi is an eigenvector of the previous matrix. Multiplying by A is a transformation. And multiplying it by 1 over square root of lambda I is simply a scaling. By transformation and scaling, I can relate the two eigenvectors. So that is the transformation given in here. So they share the same eigenvalue, A transpose A, A transpose. Thus, and being positive definite, all the lambdas are greater than 0. I can take the square root. So I label sigma I to be square root of lambda I. The square root of the eigenvalues of A transpose, that's called singular value of A. Sigma I are called the singular values of A, where lambda i's are called the eigenvalues, the Gramian. Are you all with me now? I also want you to remember that if lambda is an eigenvalue of A, lambda square is an eigenvalue of A square. How many of you know that? That's right. So let me do that quickly. Ax is equal to lambda x. So A square x is equal to A times Ax, and this is equal to A times lambda x. This is equal to lambda times Ax. That is equal to lambda times lambda x. That is equal to lambda square x. With me? So if you multiply a matrix, the eigenvectors do not change, the eigenvalues get squared, cubed. Everybody? That's right. So here I am talking about square root. Everybody? So eigenvalue, singular value, Gramian, positive definiteness, A being non-singular. Everybody? All these concepts are related, are intertwined in here. Now I come to the important topic, what's called matrix norms. Matrices are objects. Every object must have a size. The size of a number is given by absolute value. The size of a vector is given by the norm. We talked about 4, 5 different types of norms for vectors. Likewise, we are going to talk about different types of norms for matrices. So let A be a n by n matrix. The norm of A is the measure of the size of A. There are various kinds of norms. The first and the simplest norm is called the Frobenius norm of A. That is denoted by the norm symbol with A and a subscript F, and that is simply square root of the sum of the elements, square root of the sum of the square of all the elements. With me? So this is more akin to the Euclidean norm for vectors. Frobenius norm for matrices is similar to the Euclidean norm for vectors, the square root of the sum of the squares. Then I can define what's called an operator norm. Frobenius norm, operator norm. This is also called an induced norm. What is the idea? So if I have a vector, so let's go back. If I have a vector x, if I have a vector Ax, I want to be able to compute the ratio of the norm of Ax divided by the norm of x. With me? So what is that? That's a scaling factor. Notwithstanding the rotation, what is the magnification suffered by the vector Ax when you multiply by the matrix A? So the ratio Ax divided by x tells you the impact of A on x. Everybody? Now what do I want? I want to be able to compute the 2 norm of A. So how do I define the 2 norm of A? I would like to be able to take the maximum of this ratio. Now please understand, Ax by norm of x is equal to Ax by norm of x, and that is equal to A unit vector. All of you with me? Therefore, norm of Ax by norm of x is equal to A times unit vector norm of that. All of you? Unit vector means length 1. So how do I define the norm? So let P be equal to 2. It is going to be the maximum of Ax where the norm of x is 1. Are you with me? So it is the maximum magnification suffered by any unit vector x. And what is the set of all unit vectors? They are in the unit circle. You remember the unit circle we talked about? The unit circle shapes changes from 2 norm to 1 norm to infinite norm to p norm. So now you can say how many different types of operator norms are there. For every p there is a norm. I listed the notion of a 2 norm. So operator 2 norm, operator 1 norm, operator infinity norm, everybody. So one way would be to look at the square root of the sum of the squares of the elements of the matrix. Another way would be, what is the maximum magnification that the matrix brings to a vector x when I multiply the vector x by a matrix A? One by the property of by itself, another is by the action. So by setting p is equal to 1 to infinity, we get various norms. What is the general property? The norm of the product is less than the product of the norms. The norm of the product of matrices is less than the product of the norms of matrices. So these are the two inequalities which are quite basic with respect to understanding the norms. Everybody. So how do you compute the different types of norm? It can be shown that the one norm is simply the column norm. What is that? Let's look at this now. Let's look at this now. This is the sum of the absolute values. So ai, j, I running from 1 to n, j is fixed, j is column, right? Everybody? So it is the maximum of the absolute sum of the columns. So that's a one norm. Maximum of the absolute value of the rows, that's the infinity norm. The 2 norm is essentially sigma 1, and sigma 1 is the maximum, when sigma 1 square is the maximum eigenvalue of AA transpose. That means sigma 1 is the largest singular value. You remember the singular value I introduced earlier? Are you all with me? A may not be symmetric, but AA transpose symmetric. If I saw the matrix is symmetric and positive, and it is positive and A is full rank, so sigma 1 square is always positive. I can take the square root, which is sigma 1. So the 2 norm is essentially the largest singular value, where we have already defined what singular values there are. When A is symmetric, A transpose A is A square, because A transpose is A. So A transpose x is equal to this, that if lambda x. So what is that we have now? We have already talked about that. Lambda square is the eigenvalue of A square. So the 2 norm of A is the maximum eigenvalue in the case if A is symmetric and positive definite. The absolute value of the maximum eigenvalue is called the spectral radius. So what does it mean? The entire spectrum lies within that interval when A is a symmetric positive definite matrix, and the spectral radius is denoted by a rho of A. With me? I hope you are all with me now. So if A is a general matrix, its norm is singular value. If A is symmetric and positive definite, its 2 norm is the maximum eigenvalue. You can see what symmetry brings, what positive definite brings. It's a beautiful property. Just like the vector norms, the matrix norms are related. So if I have one norm, I can bound it. If I have a 2 norm, I can bound it. So the 2 norm is less than or equal to the square root of the product of 1 norm and infinity norm. Please understand, to prove these things is a 1 semester course, but you need to know all these results when you want to deal with that. The spectral norm is less than any other norm. I did not put any subscript here. So if I say this is the general norm, rho A is the spectral norm. So spectral norm is less than A means what? The spectral norm is the lowest of all the other norms. So in summary, matrices have Frobenius norm, which is simply the property of the object, operator norm, which is the effect of the operation. Operator norm is defined for any p. P is 1 to infinity. With me? P 1 to infinity. So various kinds of norms, and they are interrelated. The interrelation between the norms are given here. Look at this now. The 2 norm can be bounded by above and below by infinity norm. The 2 norm can be bounded above and below by 1 norm, except for the, and the Frobenius norm can be bounded by the 2 norm. So what does this mean? If you prove a result for any one particular norm, I can translate the result to any other norm. That's the beauty. So choose whichever norm helps you to be able to make the proof. The next topic is called condition number of a matrix. This is a very important concept in optimization again. So let A be a n by n matrix. The condition number, which is denoted by kappa, this is a Greek letter kappa of A subscript P. P refers to the norm. So the pth condition number of A is the product of the pth norm of A and the pth norm of A inverse. Okay, that's one way of looking at it. Now look at this now. Since I is equal to A inverse, the norm of I is 1, any p norm of I is 1, and that must be less than or equal to, by this result, p norm of A, and that's equal to condition number. So this essentially tells you condition number is always greater than or equal to 1. Condition number of a matrix is always greater than or equal to 1. In principle, condition number can be anywhere from 1 to plus infinity. With me? The spectral condition number for a symmetric positive definite matrix is given by condition number. It comes from the definition. We can also show it is the ratio of the maximum eigenvalue to the minimum eigenvalue. Ratio of the maximum eigenvalue to the minimum eigenvalue. That's for a symmetric matrix. For a general matrix, non-singular matrix, the condition number is essentially the ratio of the maximum singular value by the minimum singular value. Ith singular values are given by this. You already know that, right? Singular values are the eigenvalues of A transpose or A transpose A. The condition number are very fundamental and important in trying to control convergence of matrix-based algorithms. We will talk about that later. And relation between various condition number, please understand P. So there is one condition number, two condition number, infinity condition number. The condition numbers are related by these three relations. One condition number related by K2, two condition number related by infinity, and infinity condition number related by K1. But one norm and infinity norm are easily calculable. One is the column norm, another is the row norm. Are you with me? But two condition number is very difficult to compute because I have to compute the eigenvalues. So using these, while I may not be able to compute the exact eigenvalues, but I can compute the upper bound, the lower bound, and the condition number. The smaller the condition number, better the conditioning of the matrix is. With me? And we are going to show the impact of condition number in the next couple of slides. So relation between condition number and determinant, one does not imply the other. So if you took a matrix of diagonal matrix all half, the determinant of that is 1 over 2 to the power of n. But the condition number is 1. So as n goes to infinity, condition number remains the same, but the determinant goes to 0. With me? So this goes to show that there exist matrices for which the condition number and determinant are not related to each other. If you consider an upper triangular matrix, with me? If I is equal to j, all diagonal elements are 1, or off diagonal elements above is -1, everything below is 0. If you consider this matrix B, its determinant is 1, but its condition number is n. With me? So I have two opposite examples where as n goes to infinity, in one case condition number remains constant, the other one goes to 0. Here the condition number is 1, the other one goes to infinity. So there is no correlation between determinant and condition number. Why is this important? We say in computational numerical algebra, if the determinant is close to 0, it is ill-conditioned, right? Condition number. So how do you evaluate the conditioning of a matrix? It is not given by the determinant, even though we abuse it like that. The conditioning is given by the condition number. Are you with me? Colloquially we say, if the determinant is very small, the matrix is ill-conditioned. That's very colloquial way of saying. Now we are showing that there is a concept called conditioning number, conditioning or condition number. Condition number is very indicative of the property of the matrix. It depends on the eigenvalues and singular values. And the condition number and determinants are not correlated with each other. So to be able to see under what condition the solution, computational solution becomes very difficult, depends not on determinant but on condition number. That's why conditioning is important. Condition number is important. Why? Now I am going to talk about the impact of conditioning and condition number. Let's talk about the solution, sensitive solution of the linear system. With me? I am going to solve Ax is equal to b. Now let's look at this now. When you store a number into the computer, you can't store that exactly. For example, 1/3. How it's stored? 0.3333. You chop it someplace. No matter where you chop it, there's an error. So not all real numbers can be stored exactly. So when you say I have stored A, when you stored I have stored B, you have not stored A and B, you have stored somebody close to it. There are errors. So let epsilon be the perturbation in the storage of A, epsilon f be the perturbation in the storage of B. Everybody. So when we say we are solving Ax is equal to B, we are not solving Ax is equal to B, we are solving A plus epsilon B times y is equal to B plus epsilon f. We are solving for y instead of b, instead of x. We want my y to be close to x. X is a true solution, y is a computed solution. Are you all with me now? Under what condition y will be closer to x? Are you all with me? This is not your problem, this is a problem of the computer. Why? Finite precision arithmetic, not all real numbers can be stored exactly. So the problem is dirty as soon as you enter the computer. You perturb the problem. So epsilon b and epsilon f are the perturbations of the matrices and vectors. Epsilon is a small number. So what is the relative error in the solution? The norm of the difference y and with x with a true solution. X is a true solution, right? True but unknown. Y is the computable solution. So the norm of the difference divided by the true solution, it can be shown, is less than or equal to kappa A times. What is kappa A? Condition number. Times epsilon times. So what is this? The ratio of the norm of the perturbation to the original. The ratio of the norm of the perturbation to the original. Epsilon is a constant value. Epsilon is small. So even though this quantity can be small, it can get amplified by condition number. So if the condition number is small, the error in the computer solution will be smaller. If the condition number is large, the error in the solution will in general be large. Are you with me? But what we colloquially say, if the determinant is very low, you are going to get into trouble. We just showed a minute ago, determinant and condition number are two different things. And what exactly defines the quality of the solution is not the determinant but the condition number. Unfortunately, in the first course in linear algebra, in the first course in computational linear algebra, they don't tell us. With me? So what is the most well-conditioned matrix? Identity matrix. Condition number is 1. The smaller the condition number, better conditioned it is. Better conditioned it is. That means since condition number is greater than or equal to 1, errors in A and errors in B are amplified. Are you with me now? Errors in B and errors in A are amplified. So the larger K of A is more sensitive to the solution. Sensitive means what? Even small errors can be amplified. Small errors in the input can be amplified at the output if K if kappa A is large. Why? It occurs as a multiplying factor. It occurs as a multiplying factor. Everybody is in my place. Therefore, in problems, if you are going to have trouble, the first place to check is to check the condition number of the matrix. And what is the condition number? The ratio of the maximum eigenvalue to the minimum eigenvalue. If the minimum eigenvalue is very close to 0, the condition number is going to be infinity, in which case your system is very sensitive. Even a small error can explode on your face. With me? That's right. With that, I come to the end of this module. I'm going to give you lots of computer exercises. First thing, give an example of two matrices A and B such that AB is not equal to BA and AB is equal to BA. If AB is not equal to BA, in all cases we say is non-commutative. Even if there exists one example, then you cannot say the multiplication is commutative. So matrix algebra is a non-commutative algebra. Inner product is commutative. Are you all in my place? That's right. Verify AB transpose is B transpose A transpose. Verify trace of AB is trace of BA. Prove that the determinant of A inverse is 1 over the determinant of A. I've given you a hint on that. Verify A is equal to cosine theta, sin theta orthogonal matrix. Then what is that I would like you to do? I would like you to so pick A as 1, 1 and plot y is equal to ax when theta is 30, 60, 90, 120, 150. You can actually see the action. Verify AB inverse, A inverse of AB is B inverse A inverse. Verify A plus, that means I said this is the formula given by Moore-Penrose in the full rank case. Substitute this in the 4 conditions that Moore-Penrose inverse has to satisfy. Verify that this formula satisfies that. Everybody, are you all with me? These are basic nuts and bolts. With this, we come to the end of the module on matrices. It has taken a little longer, but I have covered a lot of land. With me? I covered a lot of real estate in the matrix theory.